Hey guys, so this is going to be kind of a review of what I'm hoping you learned on the gizmos. So I'm going to kind of go through not so much the gizmo, but what the gizmo was supposedly wanting you to kind of accomplish as objectives. So in the weather one, it basically wanted you to be able to make measurements using blah blah blah, observe and record a variety of weather at different locations, and then use graphs and tables to compare weather conditions during winter, summer at different locations, specifically the Pacific Coast versus Great Plains. So somewhere located along the ocean versus somewhere in the interior of the United States, and then the Arctic Circle, so pole regions, and then the tropics, so equatorial regions. So really what we were doing was comparing near ocean versus middle of continent, and then Arctic Circle versus middle of, or end of globe versus middle of globe. That was kind of, and really this sets up the climate. But what we should have found out is really this is the most important stuff, and this is kind of where I'm going to be spending time with the quiz. But basically, on a global scale, the factors that cause temperature differences and influence weather patterns include these things. So areas near the equator experience more direct sunlight than areas near the poles. Okay, and that's what's really going to be important, because that is going to drive ocean currents and wind currents. Tropical regions tend to be hotter. Polar regions tend to be colder because there's more energy input at the poles than there are at the tropics, more energy input at the tropics than at the poles. Sorry, I think I got that wrong. Anyway, so as latitude increases from the equator, remember is 0, and then we go up towards the pole. So as that latitude increases, the input from the sun decreases, and that's what causes polar regions to be colder, tropical regions to be hotter. Now, there is somewhat of a exception to that. Polar regions can get hot, but it's just in the summer, and that's when the sun input has longer to put in that less intense sunlight. So remember, in the summertime they will experience almost 24 hours of light in some cases, and so since they're experiencing so much light, that temperature can rise, sometimes even crazily enough into the 80s, but it takes a long time for it to get there, and that's because the sun is out all day long. Then this next point, areas of higher elevation tend to be cooler than areas of lower elevation. I would hope we know that, but as you travel up a mountain, it gets colder. As you travel down the mountain, it gets warmer. Now, what that also does is, as air travels up over a mountain, it cools and condenses out water, which causes rain or snow or whatever type of precipitation you want to look at. And then as that air continues to pass over the mountain, it begins to warm, and then will carry less moisture in it. So typically one side of a mountain, usually the side that the winds typically prevail from, will be wetter. The other side will be dry, which just goes into the water cycle a little bit later. And then this next point, land heats up more quickly and cools down more quickly than the oceans. We already talked about this in specific heat. Remember, water has a high specific heat compared to land, so water will heat up much slower. It takes in a lot of sun's energy and then doesn't change temperature. The land will take in the sun's energy and then change temperature quickly. So what that causes is air over water will be cooler than air over land. And so that's going to create some interesting things that we'll talk about when we talk about wind formation. But let me get this out of the way. But the other important thing on this point is that on a larger scale, inland areas tend to be warmer than coastal areas in the summer and colder in the winter. So if you're on the coast, so your San Francisco area, you've got the influence of the water from the Pacific on your weather and climate, and so that keeps you relatively stable. We talked about water acting as a thermostat before, so if you're close to water, you can have basically that thermostatic effect, which keeps temperatures stable. If you are in the interior, so you're landlocked, then typically your air is coming from areas that were already land and doesn't have that cooling effect from the water or the warming effect from water if it's a cooler season. So you tend to heat up faster, cool down faster, so you see more temperature swings, if you will. Your temperature is not as stable. Then ocean currents and ocean temperature are also influenced by climate. We'll talk about that a little bit more. We'll get into currents and stuff in great detail, but basically the sun's energy input into the oceans is what is going to cause, into the oceans and atmosphere is what is going to cause ocean currents. And we'll talk about that in greater detail later, but the intensity of the sunlight that is input will drive those currents. So that's really, really, really important. So important that if I were you, I would probably try to maybe make that red, right? So I'll leave that there for a second in case you want to see it. So that when we looked at this, weather is just the meteorological events that can be observed at a location at any given moment. So if we walk outside right now, we could observe the weather, right? That doesn't necessarily mean that the weather we're seeing right now is typical of our climate, right? Our climate is going to be kind of an average of what the weather is typically like in a given year, and that allows us to if we know the climate, we can predict what we would think the weather might look like at any given moment. Now, obviously, we can't predict the weather extensively, but if we know it's July in Denton, then we can predict that there's a good chance the temperatures in the morning will be in the 70s, the temperature in the evening will be in the 90s. There may not be a lot of rain if we're in July, so it might be drier. And so we can make generalizations of what we think the weather would be. Now, obviously, there's outliers. We've had July days where it's 72 degrees for a high, right? A weird cold front comes through. But on average, over the last 100 years or so that we've been keeping data, on average, we would expect that the temperature would be in the 90s. So the climate allows us to kind of predict what the weather events might be in a given location at a given time. So let's dive into that. Basically, on the gizmo, it basically said that you would understand what climate means and distinguish climate from weather. So weather is a distinct observation at a given moment in time, and then climate is the kind of average of what all the weather typically is at any given time of the year at a given location. Then you were supposed to analyze and compare graphs of climate characteristics, temperature, precipitation, wind speed, humidity at different locations, and then determine the effect of latitude and proximity to the oceans on local climate, or on the location's climate, and then show how plant and animal adaptations are related to climate. So this, I wanted to throw this in there because this actually will relate to aquatic environments as well. If we know the climate in an area and we can predict what the aquatic system will look like in that area, then that can also help us predict what types of animals or organisms we could see in that area. So understanding the life zone of aquatic systems relates to the climate, which then relates to the organisms that live there. So for example, you might have very similar aquatic systems that are in very different climates, and we would then expect to see very different organisms that inhabit those environments. So let's dive into the key points here. There were several factors that it's kind of the same as weather, right? So latitude, or the distance from the equator, has two effects on climate. Let me move my face. At high latitude, so up near the poles, sunlight is lower, so there's less intensity, right? So we're going to have average temperatures that tend to be colder. Higher altitudes will also have a greater variation in day length. So remember, in the summer months, the poles will experience long days, short nights, right? And then in the winter, it's the opposite. Basically, in the winter time, we get really cold temperatures because there's almost no sun input, and then in the summertime, we can get really warm temperatures because there's a lot of sun input. So that gives us wide-ranging seasons, as it were. We can't get stuck that polar regions are always cold, because that's not the case. In the summertime, it even says here, you can have July temperatures that are very similar in very different locations from the equator. So in this one, it talks about Miami and New York. New York is 36 degrees colder than Miami in the January, but then in July it's only 7 degrees colder, and that's because New York is getting more sun input in the summertime, so it has the ability to heat up. So anyway, moving on. Elevation is another one. So talking about the mountains again, right? The distance above sea level, temperature is going to decrease, right? And then the lower or closer to sea level are, the warmer it will be. So typically, the warmer you are the colder you are as you go up, the wetter you will be if you are on the windward side of a mountain range. So if the wind prevails from the west and you are facing that wind coming in, then typically you will be wetter than the other side of the mountain as the air passes over. It basically squeezes the moisture out of the air, and then as it goes on, it's drier. So that can lead to kind of monsoon type areas on one side of a mountain, and then desert areas on the back side of that mountain. If you want to research that a little bit more, there's quite a few places where this happens in the Rocky Mountain areas. Walden, Colorado is a pretty good example of one. It's kind of surrounded by mountain ranges, and the wind prevails kind of from the west or northwest, and so Walden is this area that's much drier than the surrounding mountain areas. But anyway, water temperature rises and falls much more slowly on land or air than temperatures. Again, that's talking about the thermostatic effect. So San Francisco will have a really moderate climate, and then the interior, somewhere like Nebraska, will have a really crazy, wild swinging in climate. And then if we take that even further into the desert areas, you'll have even wider swings of temperature. Places like Phoenix, Arizona, or Albuquerque, New Mexico, which, no, that's not as bad, but it is a desert environment. So anyway, it's at a higher elevation. Global wind patterns will also be affected by this. So basically, the input creates the global wind patterns, and we'll talk about wind later, so don't worry too much about this. But basically, getting those global wind patterns set up will actually affect climates in different areas. So the interaction of all of those things lead to climate. So you can see how it can be crazy, because you have, like, say, San Francisco that is on the Pacific Ocean, so it's got that thermostatic effect of the ocean, versus, say, Los Angeles just to the south, which is also pretty close to the ocean, but it's in more of a desert region, and so it typically has a much different climate than San Francisco, even though they're pretty close to kind of similar areas of the globe, if you will. So notice that there's lots of things that can change climate, so you can't just look at one thing. Like, you can't just say, okay, latitude is, this area is near the equator, so it's tropic. That isn't necessarily the case. You could have a huge mountain range near that area, which then causes, if you're on the mountain range, it could cause you to be, if you're on one side, drier than the other, or cooler than lower elevations. So all of these factors come into play and then create really both weather and climate. So if we look just a little bit more at the adaptation thing, basically many plants and animals will have structures that help them survive in areas based on climate. So a lot of these are climate specific deals that help them survive. So for example, polar bears living in the tundra will have white fur with a layer of fat underneath. That white fur reflects the sunlight. Actually, that doesn't make sense. Polar bears have their hair is actually a filament that brings more sunlight to their skin. Their skin's actually darker, which actually absorbs more sunlight, so then they're kept warmer. But then that layer of fat also protects their internal organs from getting colder. So they basically are wearing a big fat coat, quite literally. And then other adaptations are indirectly related to climate. Like in Mongolia, there's a lot of grasslands where it's advantageous for birds of prey, especially, to be able to see very acutely into those areas so that they can see their prey from long distances. This also applies to aquatic environments. In the ocean, for example, in polar regions, seals will have that same blubber that basically keeps them warm. And then if you're in oceanic, like coral reefs, some sharks have really keen eyesight that helps them see critters on reefs. So all of these principles can be applied to aquatic environments as well. So what I hoped you saw through all of this is that sun creates weather, weather establishes climate, climate gives us life zones that then organisms fit into. So the main difference between weather and climate is that weather is going to be the condition of the atmosphere at any given moment in time. So if I walk out right now, what is the atmosphere doing? Is it raining? Is it cold? Is it whatever, right? So that is my weather. Climate is typically going to be an average of what the weather has been at a given location over time. So here in Denton, Texas, we have distinct climates. We have a climate in the summer that is typically hot, relatively dry, and then we have a climate in the fall that, if you can call it a fall, but we have a fall where it gets cooler, the days start to get shorter, right? And then into the winter it's cold, but the days can be warm, and then etc. You get the idea. And then we kind of have that monsoon season in the springtime. So it's an average of all the weather. Can we predict perfectly that what the weather will be based on climate? Not necessarily. I mean, we always have those outlier days. Like a few Christmases ago, we had 96 degrees and tornadoes on Christmas. So the weather that day did not match the climate. But typically, if we looked at a set of weather data for a particular day, if we average those out, they would fit within the climate. So weather is moment, climate is average of all the moments in a given time frame. So I hope that helps. Really, the main thing we're looking at here is how the sun inputs its energy into the environment, what that is going to do to numerous factors that will then affect life zones within aquatic environments and characteristics of organisms within those environments, or adaptations of organisms within those environments. So that's where we're headed. Next, we'll be moving on to some other things. So